In this video, I'll explain how to create a pseudo-random number generator Axi-Lite IP and how to connect it to the processing system, all in Vivado software. Let's get started. So I'll start off by creating a project. So before I get started on the project specs, I want to note that the Vivado version I'm using is 2021. That is 2020.1. The reason is because I'm going to use PYNQ version 2.6, which is compatible with this version of Vivado. We need to pick a name for our project. I'm just going to call it Zor Wow _PRNG. The reason I'm picking this name is that ZorWow is a pseudo-random number generator model, which I will be using for this purpose. So if you look at Wikipedia, I can actually pull it up here. We can take a look at this ZorWow thing. So there is a class of pseudo-random number generators that are very simple. They are called ZorShift. And ZorWow is an implementation, or rather an extension of this ZorShift pseudo-random number generators. As you can see, none of these is ZorWow. Oh, okay, here. It's very simple. This is a C code that is implementing it. You need an initial state, and then it will just loop after this number. It also says that this generator is the default for NVIDIA's CUDA toolkit. I don't know if it's still the thing, but because it's very old. But that's interesting. That means it's a legit pseudo-random number generator. Why would you need such a thing? If you're doing anything like a Monte Carlo simulation or any type of computation where you need a random number generator, then this is where this thing is going to come handy. What we are doing is that we are going to implement this in hardware and basically use PYNQ to call our pseudo-random number generator IP and generate random numbers on demand. So that's what it is. And I call my project name ZorWow because that's a random number generator I'm using. Then next, it's an RTL project. Sources we don't need to add right now. No constraints. And here we need to pick a board. Well, a part or a board. I will pick PYNQ Z-1 because that's the board I'm going to be using. PYNQ Z-1 uses a Zinc 7000 lower end Zinc 7000 FPGA, and it's also one of the cheapest. Project summary, I think everything's fine here. The next thing after creating a project is to create a block design, which is simply done by clicking on Create Block Design. So what happens here is that we can drag and drop IPs into a graphic interface and create a diagram of our circuit. Makes things a little bit easier. The first thing we're going to need is a Zinc processing system. So Zinc 7000 series is basically an SoC, which in this context means it's a microcontroller and FPGA resources to create your own circuit. And then you can also connect it to the microcontroller, which is these ARM cores. We're using one here. Then it just assists you with creating the block design also. As you can see, it says run block automation. By running it, it shows you what it's going to try to connect to what. Just say OK. So right now what you have is your processing system connected to the memory and the fixed IOs on the board. And how does it know how to connect them? It probably came from the board files. So the next thing to do is to create our own IP. Yeah, we go to Tools, Create and Package New IP, which is this one. We click on it, and it brings up this dialog box. We say Next, and here we pick what kind of IP we want to produce. We want to generate an Axi peripheral. So Axi is basically an intra-chip communication protocol through which we'll be connecting our microcontroller or the processing system to the random number generator. And we click Next. So we have to pick a name for it, and I will pick Zor-Wow Lite. I call it Zor-Wow because that's what it is, and Lite because we are going to use an Axi-Lite peripheral. So by default, it's Axi-Lite. As you can see, it has other options such as full and stream. The thing is, if you are actually doing a serious Monte Carlo simulation hardware, then you probably want Axi Stream. Depends on how you're doing it. You probably want Axi Stream because you want to create or generate blocks of random number and then pass it to the processing system to work with. But for our purpose, we just want to read them one at a time and check a bunch of things. We just use Lite. The width of the registers are just 32 bits. And for the number of registers, I pick 7. And I'll tell you why in a few minutes. So the next thing is to pick what we want to do here. Are we going to edit the IP? Yes, we are going to edit the IP because right now what it's going to do is just going to create an IP with without any particular hardware inside. It's just going to be the Axi peripheral hardware, but no random number generators. That's the part we need to add. So we pick Edit IP and Finish. What it's going to do is that it's going to create yet another project by itself. Vivado is going to do it. And in that project, it's now this new project is the IP that we were developing. So you have the wrapper, which is this. And in there, you can see that there are like the Axi-related parameters defined, and then the signals. And it has, within it, it has instantiated your Axi IP and connected the relevant signals to it. And the Axi IP is this guy. So here is where we are going to do our work. And for that, we need our Zor-Wow pseudo-random number generator. Before I do that, I want to basically show you how I have done it. Well, I can do it after I did it. So I'll add the design sources. Add files. Okay, so I have these two files. One is Zor-Wow PRNG system Verilog, and then the other one is Verilog. I have these two just because I wrote my Zorval in system Verilog. And in order to instantiate it in the Verilog code, I thought I'm going to need a Verilog wrapper for it. I actually may not. So I'll just add the Zorval PRNG SV. And that's it, finish. So that's now one of our design sources. As you can see in the hierarchy, it's not underneath here because we haven't instantiated it anywhere. But let me show you what it is. It's basically getting a clock, a P signal. I added this P signal as pause to pause the generation of random numbers. And L, which is a load signal, which basically means to load the seed. A reset signal. And these X0 to X4, which are the state signals. So we can use these initially to initiate our random number generator, or in other words, to pass a seed. And then there is an output signal, which is basically the 32-bit output. So that's why I had 7 registers. Essentially, I needed 5 for the states, 1 for the output, and I'm using one of the registers to basically pass these P and L signals. That's essentially why. I know this is not the most efficient way of doing it, but this is probably the easiest way of creating the Axi IP. So the way I do it, I have a state machine with 3 states: the pause state, the load state, and the generate state. And the rest is essentially like the C code. For the pause state, what I do is that I load the current state into the next state, so as in this state doesn't change. The load state, you can only load when you pause and load. That's how I did it. And basically, it reads the new state from the registers. So let's say you passed a seed, you generated a bunch. Now you want to change the seed. You pause and load. And then the generated state, which is that's the part that resembles the C code. So when in the generated state, it just creates the newest state from the previous states and keeps going until a load or a pause signal is seen. So it checks for these to see if it's going to go to a load state or to a pause state. Otherwise, it's going to stay in the generated state. So that's what it is. Now I'll show you how to connect this IP to our instance of Axi-Lite slave. Now that we know how the Zorval random number generator works, let's basically connect this to the rest of the Axi IP. So I just go here, and at the bottom of this file, which is this file, at the bottom of this file, I'll add where it says add the user logic. I basically instantiate my IP. Since I don't remember the names of these, I just copied it from there, and I'll delete the parts that I don't care about. Okay, now that those are deleted, I will just name this PRNG and add the respective signals here. So for the clock, I'm just going to use the Axi's input clock. So we'll go up here and find it, which is this. For the reset, I'm also going to use the Axi's own reset. here. Okay, so as I mentioned earlier, we are going to use the slave register 0 for these two signals, namely the pause and load, and the other 5 from 1 to 5 basically for these state parameters x0 to x4, and the last one for output. And that's exactly how I'll be connecting them here. So for this, we just need 1 bit of this slave register 0. I'm going to use the first bit. I'm also going to use the second bit for load. And then the rest of the bits for this slave register 0 are going to, we don't care about them. So they are going to remain useless. I'm going to connect the rest of the signals to our instantiation of XOR-WOW random number generators, and we'll get back to you. Okay, now I'm done connecting all of those signals. As you can see, I did not instantiate any new signals or any variables or anything. I'm just using the bare IP and just connecting the registers to the inputs and outputs of my XOR-WOW code. And as I mentioned earlier, the first 2 bits of the slave register 0 are going to be used for pause and load, and we take care of these through software later. As to how we are going to actually implement this in software, I'll show you later. And then the state registers x0 and up to x4 are loaded from the registers slaves 1 to slave 5, and the output is going to go on slave 6. And one thing I want you to notice is that after you Control S, or basically save, you will see that this random number generator that used not to be under this hierarchy is now under the XOR-WOW Lite V1 whatever, and that's because it's now we have now instantiated it. We call that instance PRNG, and as you can see, the name is here in the type, or the type of circuit is this, and yeah, we didn't actually need the Verilog wrapper for this. We can just instantiate the system very well here. So the one more thing that I would like to do is to I don't want to run any simulations or anything because it's very simple. We know it works. But one thing I'd like to do is to open Elaborate Design, which basically will show us a schematic of this whole circuit that we built. And we just want to make sure that all of our connections are correct and we didn't make any stupid mistakes. Okay, the elaboration is done, and we got this error, which reminded me that I made a mistake here. We cannot just connect this SLVREG6 to the output because it's basically an input. So what we have to do is to basically define a new signal. I just define a new wire here. Call it wire and we call it output underline PRNG. And the length of this has to be 32 bits. So we say 31 all the way to 0. Okay. Now we get this and connect it to our out signal or out register here. So that should do it. Now this output PRNG should also connect to here when we are reading the registers with our Zinc processing system. So when we are reading the output data, we want to read it from the 6th or 7th rather register. So we just output it here instead of just reading the 6th register back to the output. We will use our output, which is the one that comes out of here. Okay, now that should do it. And I'll do the elaborate design one more time, and this time it should work out. Okay, so after elaborating the design, we'll see this block, which corresponds to the top level in the hierarchy. We open it, and you'll see a bunch of things. We'll want to see our connections. So this is our ZOR-WOW and the connections. So the slave registers are connected to where they're supposed to be. Number 5 is this one. And the output is connected to this multiplexer. The next thing you do is you are going to go to this package IP tab. We are not going to do anything specific here. We just do merge the changes. It's done. And then review and package. So click that. Whatever, yes. Okay, so it's done. And I believe it automatically adds your IP repository to here. So we'll go here and we try to see. Yes, it's there. So ZOR-WOW Lite version 1 is there. And now we can add it to our design. So as you can see, it's like a generic Axi IP, but it of course has all of the stuff that we created in it. And I don't think you need to do anything specific here other than just run the connection automation, and it should take care of it for you. So, okay. But as you can see, it generated a bunch of things. One is an Axi interconnect. You could actually drag and drop it yourself also, and then do the connections, or you could use this. And it connected to your Axi interconnect to the master Axi from your processing system, and the output goes to, or the master Axi from the Axi interconnect goes to your ZOR-WOW IP, and that's how you communicate or you interact with this. And there is also this thing that generates the reset signal from the processing system. So this looks all good, and we can just synthesize and generate a bit stream. I'll just click the generate bit stream. Well, I first save it and also validate it. It looks fine. And then I'll just go with generate the bit stream, which starts off with synthesis, implementation, and generation of the bit stream. So it will take a while. I'll pause the video while this is being done. Okay, again, we got an error. That's because I basically forgot to create the VHDL wrapper for our design. So that's one thing we need to do because this is not something that can be compiled, of course. So we create an HDL wrapper. That's important. And by the way, if you're wondering, I'm actually doing it as we go, so I didn't I didn't really plan for these errors, but these are the mistakes that I think naturally anyone can make. And so we let Vivado take care of it. Okay, now the wrapper is generated. We let for it to update. Now, as you can see, this thing basically shows that it made the hierarchy for you. And now we do the generate bitstream one more time. And again, it's going to take a while, so I'll pause the video. So after the bitstream generation is complete, you'll see this menu popping up where you can look at the reports and everything. One thing that you probably want to look at is the timing report and see how the forced negative slack is. But we don't really care about such things here. So I'll just leave it as is. And the next step is to take this on the FPGA board. In order to do that, what you need to do is to get the bitstream file, which is the .bit file. And we also need the .hwh file. Which is here. So these two should have the same name when we want to take them to the PYNQ board. So I will call both of them Zor-Wow. Same as this one. So in my case, my PYNQ board is already connected. So all I need to do is to just go to it and take these to the board. If you're familiar with the PYNQ board, you already know that there's going to be a Jupyter notebook running, and you can simply put your code on there and start put your bitstream file on there and start coding. So I'll create a new folder. I call it Zor-Wow. And then I'll upload my bitstream files. And I open a notebook where I'm going to code up my driver. Now I start off with doing the imports. So from PYNQ, not from. I import overlay. I think that's all I need. Maybe I'm going to need my matplotlib also. Just so I can plot stuff. That should be enough. So now I'm going to create an overlay for our, well, I'm going to basically create a new class where the overlay class is going to be the parent to make the driver for our random number generator. So let's call this class ZOR-WOW. And let's see, do I need any inputs to this? Well, I need the path to the overlay. I also need the seed values. So let's call them just want to load the overlay or load the bit stream here. And I need a reset. I'm going to fill up later. I also need a generate. And we also need a load function, probably. These namings are in line with what I had in the hardware. So we generate, we reset, and we load in case we wanted to change the seeds. And in case of load, we need a new seed, otherwise it doesn't make any sense. So I just pass seed arguments to it. So now we need to fill up the these places with the code. So we earlier mentioned that we are going to use the register 0 as the control register, and the rest of the registers as our data registers in order to pass the seed and read the output. And so we are going to fill them up accordingly. Now, since I do not remember how I name my IPs, as in I can simply go and check it online, I mean on Vivado, but I'll just use the base overlay class to load the IP and see what the name of the Axi peripheral is. So just it's ZOR-WOW that fits. Load the IP. And so we call this ZOR-Lite _0. And so we are going to just use this name to write to the registers the values of our seeds. Okay, so the first register we said is going to be used for our control signals, and so we have to start feeding in the seed from the second register. The second register is going to be our so each of these registers are 32 bits, and the way we are counting them are by the number of bytes. So the second register is going to be at address 4, which is 4 bytes. So address 4 is going to get seed 0. And the same way we feed the rest of the seed values. I'll pause the video and come back when I'm done with this. Okay, so here we have a small code snippet which basically loads the registers. The other thing we need to do is to set the control signals to pause and load, basically, before we put these seed values into the register. So we'll just add that here right before the for loop. And so as I told you earlier, we're just using the first 2 bits of that very first register. So out of the 32 bits, we're using only 2 bits. And those 2 bits, we are going to set them to 1. So it's going to be in the pause and load state. And 1 would be basically 3, as in it's 1, 1 in binary, which is 3. So here we set it to load and pause. And then we load the seed, and that would be our init. So that's our initialization. We are not going to start until, of course, we go to generate. Now there is one more thing that I forgot to do. Because we have a reset function, it would be better that if we keep these values somewhere. So what I'm going to do is to make these available for reset. Right. Okay, perfect. We have them. Well, not perfect yet. Three, two, one. And so when we can write the reset function essentially the same way as the init function. I know what I'm doing is a little redundant, but already done it that way. So as I said, I'm doing this on the fly. It might be redundant. Okay, now that we have it this way, I actually think it probably would have been better if we called the reset function here instead of doing this. So instead of these, I'll just do self.reset. And that takes care of it. Okay, so the next thing is to create our generate function. The way I was thinking of doing it is to basically send the change the first 2 bits of the first register. So it won't be, it would be 0, 0, not pause and not load, but rather the generator state. Then I read my value and then I put it back to pause. So here is how I'm going to do it. Okay. So in the generator state, what I'm going to do is that and since I did not define this as an object variable, I'll just use the number here. Okay, so here we just set both of them to 0, so not set to load and pause anymore. Then what I'm going to do is that I'm going to read the 7th address. And it's like this. And the 7th address would be, I believe it would be 4 multiplied by 6, which is 24. And we call this out. Then after this is done, I'm going to set this back to pause. And I believe pause state is just 0, 1. It might be 0, 2, but we'll check. So, and I return the generated value. And last is basically the load, where we can change the generated random number. Sorry, the seed of the random number generator. So I'll just quickly implement this as well. So now here's the thing. Do we want to change the seed values? Or yeah, we probably do. We probably want to also change or have a set of new seed values. So I'll just repeat what we had in it here. Looks good. Now, instead of the original overlay class, we're going to use this guy. And we are missing some arguments. So, okay, one thing with respect to the XOR wow is that you cannot pass 0 as seed, from what I remember. You have to pass something else. So I'll basically do that. And we got an error. Let's see, what is that error? Oh yeah, here I use the rec address, and elsewhere I use base address. I don't know why. One more time. Okay, now we have our overlay loaded, and let's now see if we can generate some random numbers. Okay, so I just noticed that we are generating 0, which is not we wanted to generate. So I actually checked directly from the OL to see maybe there is something wrong with the code. And then I noticed that in my XOR wow code, I mistakenly have used an active high reset, while the reset is actually active low. I'm going to fix that and generate the bit streams again, and we'll run the same code with the new bit stream, and hopefully it's going to work. Okay, now I have updated the bit stream with the random number generator's reset changed such that it will reset on active low. And let's see if we manage to fix the problem. It seems that we have fixed the problem. Yes, so we can generate random numbers. Now, I don't run any serious quality assurance thing, but I will just produce a list of random numbers, and we'll just look at how it's distributed by eyeballing simply. So let's just produce a list, R&D list, and let's say a for loop length 1,000 maybe. And if you don't know that much Python, what I'm doing is just generating a list of random numbers. I'm going to reset my generator first. And I'm going to make a list of the length 1,000, and then I'm going to basically look at its histogram or something. In the meantime, plot is tracking. So as you can see, it's pretty slow, and that's just because of how we implemented it. We have used basically an Axi-Lite IP, and we can only read one number at a time, while the Zor-Wow generator itself, considering that our clock speed is 100 megahertz, is going to produce one new random number at each clock cycle, but we can't read it at that speed. Okay, so this is our histogram, and it looks fairly uniform. I'm pretty happy with this. I'll post the code and everything, bit streams and everything on GitHub along with the video. So thanks for watching.